Hello, everyone. Welcome back to CSAIL Office Hours. I'm Daniela Rus, Director of the Computer Science and Artificial Intelligence Laboratory at MIT, CSAIL. And today we are going to talk about all things generative AI. I'm joined by some brilliant researchers and colleagues at CSAIL, as well as Greg Huang, business editor at the Boston Globe.
So today we'll be exploring the cutting-edge field of generative AI. This is artificial intelligence systems that can generate new content like text, coding, images, and videos from scratch or with inputs. Now, work on generative AI has deep roots here at MIT dating back to the 1960s. Today we're going to get into the cutting-edge research that's happening in this field. We've seen a lot of rapid progress in recent years. Systems that can write stories, code software, generate photorealistic images, videos, and more. So to discuss the latest research in this area, I'm joined by 5 experts from MIT CSAIL, whose work spans different aspects of generative AI, including robotics, language models, coding, images, and video generation. Before we dive in, we can do a quick round of intros.
Sure. I'm Armando Solar Lezama, and I work at the intersection of programming systems and AI, particularly focused on programming technology.
I'm Jacob Andreas. I work on natural language processing and computational linguistics.
Hi, I'm Yin Kim. I work on natural language processing and machine learning.
Hi, I'm Philip Isola, and I work on computer vision and machine learning.
As you all know, generative AI has seen rapid progress in recent years, so leading to systems that can write creative stories, code software from natural language descriptions, generate photorealistic images and videos, and much more. It's also led to a reshaping of the global tech landscape, with the rise of OpenAI, NVIDIA, and just billions of dollars being poured into chips, cloud servers, software development, and just really a war on talent. We're joined by people who know the most about what's happening here in Gen AI at CSAIL. And your work all spans these different areas, right? So from language and coding to images and robotics even. So I'm going to just jump in with some questions. Because the LLMs have been such a huge explosion in interest in recent years, I'm going to start with the language guys here. So Jacob, your work on this compositional and grounded language understanding, it's demonstrated the ability to translate between natural language and structured representation. Maybe you can talk a little bit about what that means, but how do you build these generative AI systems that can generate these natural language descriptions?
One of the interesting things to see has been, when we started working kind of at the intersection of language and vision especially, it was all about getting these sort of carefully curated data sets of, images paired with captions in natural language, or images paired with questions in language and answers to those questions, and thinking very carefully about the design of kind of specific neural network architectures that could map, directly from images to text or from text to images or whatever. And I think the biggest thing that's changed now is just that what research looks like is much less about how you specifically design some specific neural net for this little task, or even how you go out and collect, paired data just for some target task of interest like image generation or image captioning or whatever, and much more about, I think on the data side, thinking about the kinds of, general data sources and properties and structures and data sets that induce shared representations in these models of, not just language and not just vision, but also kind of the world that underlies these things. And this is something that I know Philip is thinking a lot about lately as well. But yeah, really just less about how you solve any individual problem and more about how you collect the kind of data that gives you the kinds of representations that really let you do anything. Talking about starting to generate text, generate images, things like that, I think one of the other big challenges now actually has less to do with the machine learning side of things and more with just kind of the human-facing side of things. And because LLMs are so powerful and because we're have such a good language processing toolkit now, I think everyone's kind of adopted this paradigm where you try to describe whatever it is that you're trying to accomplish in natural language. And sometimes language is a great medium for specifying what you want a picture to look like or what you want a piece of code to do. Sometimes it's not the right tool at all, and I think we're still figuring out just what the human interaction story should be here, and what the right way of communicating with these sorts of generative models is.
And you, being a language expert as well, how do you react to that, and then how do you improve things?
Just to react to that, I think when Jacob and I were PhD students, there was a lot of work on you wanted to model the translation process, you wanted to do a natural language processing task called semantic parsing, and you would craft models and data sets for this task of interest with the hope that it'll be useful for some downstream task of interest in the future. But now we have these systems actually working in practice, large language model-based systems that are monolithic data-driven models trained on lots of data sets, but they're working well enough that they're being sort of like a core part of major AI-based services today. As you think about how these systems sort of like the entire pipeline of their systems, from data collection, from the systems on which they're trained, how they're used, how the outputs of these systems are sort of presented to the actual users. I think there's a rich sort of set of research questions that sort of like weren't really a core part of NLP, I'd say, until these technologies came along. And I think that's where a lot of the interesting research questions are.
To me, the fact that you can put AI in the pockets of everyone with the use of natural language processing and large language models is absolutely extraordinary. We have truly democratized AI. But I'd like to follow up on Greg's question and ask you, what do you see as the most interesting or exciting applications, especially in business? I know that for the past year, companies have struggled to understand how they can get value from these new technologies, and in particular on the language side.
I think one application is extracting structured information from unstructured data with which to do further modeling, further conversion into sort of relevant services. In the past, if you, for example, had clinical notes or like contracts and you wanted to extract information out of them to do stuff with them, like build a chatbot on top of, or have a machine learning model to give outputs, then that was a very sort of burdensome process. But now it's not perfect, but if you have a large language model and you give it, for example, some examples of extracting structured data, it'll get you started. Of course, this will need further refinement, and every sort of application should be mindful of, what's the risk of getting this wrong. But I think that's sort of a very prominent application where I think LLMs will get you from 0 to 1.
What do you think, Jacob?
In the, I guess, pre-LLM era, this business of how do you do structured information extraction, how do you parse a document, how do you do good web search, these were entire sort of major areas of research, and people built these same kinds of specialized models that we were talking about, and they kind of worked. And that was really kind of like the cutting edge of what you could do. And now we live in this world where, you can kind of sort of do all of these incredible things like code generation and long-form document generation, and I think maybe part of the reason that the business world has struggled to adopt these things, which are the things that people are really excited about, is because there's still a lot of work to do and things to iron out to make them really like safe and robust and reliable. But all that stuff that we were trying to do, before the LLMs happened is just, solved essentially. And I think there's actually, we haven't even yet like really adapted to living in a world where, late 2000s era NLP technology works really, really well. Much less to living in a world where, LLMs can reliably do all the things that we're trying to get them to do right now.
How does your research right now, how does it inform, the next GPT or whatever model, we're seeing out there, or, how Google does their things you see when you start to do a Google search? Like, how close are you to that, and what's the kind of process for getting in that pipeline?
So a lot of my current research is focused on making LLMs useful through making them more efficient, interpretable, and controllable. And I think Daniela, said that it's amazing that we can access ChatGPT on our phones and have access to this incredible technology. So we have democratized access to these technologies to an extent. But if we think about like who really has the resources to develop these models, adapt them to various tasks of interest, I think there's still like a lot of barrier to really working with these models. And I think part of the problem is everything related to these models, architectures and algorithms, inefficient. They require a lot of resources. They contribute non-trivially to the carbon footprint in general. And I think that's what motivates a lot of my current research on efficiency.
Right now, you can run ChatGPT or your language model of choice on your phone, But in fact, the computation has to happen on server farms. And only big corporations have the resources to access the server farms. Additionally, when a company wants to instantiate a language model for their own needs, right now, either they get a server farm or they send their data to one of the providers of these huge models, and that has some privacy issues associated with that. So the research to make foundational models able to run on small devices like enterprise computers and phones is very important.
Well, let's shift gears to the whole programming side of things. And you read stories in the New Yorker or Wall Street Journal or Boston Globe about software developers' jobs being, not threatened, but it's changing how coding happens. Maybe you could, Armando, speak a bit about your research on that front and kind of what you see happening there at the cutting edge.
For a lot of routine tasks, and especially for a lot of tasks that involve heavy use of widely used APIs, for example, these kind of tools can make an enormous productivity difference. And especially for people who don't have kind of that deep knowledge of these APIs at their fingertips, allowing them to work at the rate of people with much more experience than themselves. I think there is the question of what kind of impact can we expect from these kind of technology. So on the one hand, it's sort of very well known in the software industry that the amount of time that one spends actually typing in the code that goes into a product is a tiny fraction of the overall effort required to design and build and then maintain software product. And I think we're still very far from the point where AI can really help with all of those different tasks that are part of a general software development framework. The other thing is, as an industry, software is, I think, quite different from many other industries. On the one hand, today we see like, wow, this is a big change in how people program, but we've seen really big changes in how people program many times, even over the course of my career. For example, when we moved towards managed languages, where suddenly it was possible to build really rich functionality just by grabbing libraries from all over the place. Like, that was a huge shift in the way people developed software and a huge productivity boost, right? That's what made it possible for, suddenly startups with 2 or 3 people to very quickly build up infrastructure and deploy services used by millions. And so we're an industry that is very used to that kind of change. At the same time, when it comes to the question of jobs, for example, if you have, a construction industry, right? Let's say that suddenly builders became 10 times more efficient in their use of labor to produce a house. Well, in order to produce a house, you don't just need labor, you need land, you need raw materials. It's pretty likely that you would need now 1/10 as many construction workers, because you're not going to get 10 times more land, you're not going to get 10 times more building materials. With software, you basically need people. You need skilled people. If you can get twice as many skilled people, you can design twice as much software. You don't quite have the same set of constraints, and we have this huge unmet need of applications that would be awesome if they existed, but maybe not at the price point that it takes to build them, or applications that exist in a way that is vulnerable to exploits, that is hard to use, that is insecure. So we have a huge unmet demand for software development that I think we're very, very far from running out of things to program.
You're talking about software that's going to, run airplanes and so forth, right? So is there, in your research, are you finding ways to, or how do you get over that? How do you make it actually work?
So for us, this is a very important area of research that we're very focused on, which is how do you combine the style of reasoning that you get from an LLM that's able to draw from this huge amount of experience from having seen basically all the code that is available on the internet, but how do you combine it with the need and the ability to reason logically about what the code is actually doing, to reason about how different pieces of code are going to interact with each other. And this is something that LLMs have proven to be not very good at, reasoning about the low-level details of code. At the same time, we do have a lot of techniques and a lot of tools for doing very precise automated reasoning over code. And the question of how do you get those two very different technologies to work together so that you can have the level of reliability that is needed for many of these really important applications. I think that's one of the big open questions right now.
There are so many safety critical systems where hallucinations and errors are just not acceptable. And so at the same time, we have an entire field called verification, whose job it is to make sure that the software that we build is correct and will execute according to expectations. Can you say a few words about where we are with respect to bringing verification into machine learning?
We do have this possibility of accessing ground truth by verifying the actual behavior of the code. The field of verification has made enormous leaps over the past 10 years to the point where today we have some really compelling examples of systems-level software that has been fully verified to prove that it's completely absent of bugs, that it's going to behave exactly as people expect, even against adversarial attacks, for example. One of the big questions is, how do we get the cost of building that kind of software down? Because right now, these kind of efforts are one-of-a-kind, very, very challenging development efforts. The big question is, can LLMs, can AI in general, help democratize these kind of technologies so that it's not just very well-funded research-level efforts, but it's every programmer writing software for embedded devices, for example, every small or medium-sized company building Internet of Things devices that can actually have access to this kind of technology. One of the challenges in doing this is that, on the one hand, we don't have the kind of enormous data sets of verified code compared to all the giant data sets that we have for things like Python. We also don't quite know how to automate a lot of the clever insights that go into making many of these verification feats possible. So this is right now an area that's really just starting to take off in the research community, but we do expect, I think, some compelling results in the near future.
Is scalability a problem?
A lot of these things work by breaking the big problem into individual chunks and verifying small pieces of software at a time. But it's actually a bit of an art right now to do things in such a way that when you put all of these verified components together, you can make these end-to-end claims about the reliability and the security of the overall system.
You're working on, among other things, image generation, creation, with all kinds of applications. I just want to get you started on, what are you seeing that's exciting on your research front?
So image generation and video generation is one of the other big areas, along with language models and code models, where generative AI has made a huge difference, and it's just dramatically improved over the last few years. So it's very exciting. I've been interested in that. I think that one angle that might not be fully appreciated yet, but it's the angle that I'm most excited about, is that the goal of computer vision has been stated as to recognize objects, to make a self-driving car that can follow a lane. But there's kind of a bigger goal behind that, which is you want to be able to generate a model of the world around you, understand where everything is, how it's moving, what it is, what it's going to do next. You kind of want to have this model in your head of the world around you. And generative AI techniques are getting closer and closer to that, especially when it comes to video generation, which is one of the very rapidly moving areas right now. If I can generate a video of the world, if I can look at a picture and say, here's what it might look like if the car turned left, or if it started raining, and I can hallucinate that, and I can generate that. This is a more positive use of the word hallucination. I can imagine that. Then I've really understood something about the world, and how would I be able to make those types of predictions and think about what might happen if I didn't have that model of the world around me. So video models right now have some ability to do that, and it's only partially there so far, but that's the aspect I'm most excited about, having a model of the world that you can actually imagine counterfactuals. What would happen if I were to look left? What would happen if the car were to dart in front of me? Would I have to stop? And then how can this lead to more intelligent agents and robots that can anticipate those futures and react to them?
How close are we to the Matrix?
Yes, exactly. This is basically the Matrix. We're far, I would say. So we have right now video models and image models that look almost photorealistic, but the physics behind them is not quite there. So if you look at the very latest video models, like there's one from OpenAI called Sora, every frame is almost perfect, but there's a famous example of people digging a hole on the beach and pulling up a beach chair out of that hole. And the sand is kind of flowing around the beach chair, but then the beach chair is kind of congealing out of sand, and an extra leg is being formed, and then it's just not physical. So every frame is almost right, but the actual world is not physically modeled accurately enough that you could really make predictions that are of the robustness and quality necessary for control. So I don't think we're at the point where you could train a robot in the Matrix, but we're heading there pretty rapidly.
Well, right now, the methods we have for generative AI are primarily statistically driven, and this means they do not understand physics. So what is the community doing to bring physics into these models?
There's a lot of interest in this. I think one approach is just to say, well, big data and big compute solved a lot of things that we didn't expect it to solve. So maybe if you just scale up statistics even more, eventually a causal model will pop out somehow. And that can happen in certain circumstances, but that's it's more speculative. We haven't seen that fully happen yet. Another approach is to inject some kind of physical constraints and mechanisms into your modeling assumptions. And one of the areas I'm kind of interested in right now is take some classical physics simulator, like a computer graphics engine of a video game, and augment it with generative AI. So you have this hybrid system that has an underlying physics engine, which we understand very well, but it's been rendered with generative AI to make it show more diversity and use all the power of data-driven methods as well.
The other thing you can do is you can take the output of a generative AI system and pass it through a simulator that verifies whether the physical constraints of the task or of the query have been met.
Yeah, definitely. That connects back to Armando with code verification. You could verify with classical simulation. You could also verify by having an agent that interacts in the world. So, if the hope is that we will have robots that have models of the world around them, then one way to verify if the model is correct is the robot takes an action and it sees what happened, and it gets feedback as to whether its predictions and model were correct.
Is the big, killer application here, is it in entertainment, like video games, AR, VR, or is it on the robotics side, or what are you seeing?
Yeah, I think that the current killer app is entertainment. And that's been the case for a few years. Everybody had a lot of fun making images of making storybooks for their children or sharing funny photos online. And I think there's a lot of applications in entertainment and Hollywood and video games. But the one that is a little bit more future-looking and that I'm even more excited about is using these models of the world as a substrate for intelligent agents, for robotics, for systems that really understand physicality, causality, that are not just statistical correlation machines, but actually have a deeper understanding of reality.
And perhaps a closer opportunity is in manufacturing, in using these approaches to do design and fabrication. using AI methods. That's the one I'm very excited about.
Yeah, definitely.
Any reactions to kind of what's the time frame for this being big in robotics?
It's already transforming robotics in big ways. I mean, we used to think about intelligence as connecting perception and action, going from pixels to control. But now with large language models, we have, and especially multimodal models that have both vision components and language components, we are moving fast forward. So what do I mean by this? You can train a robot to associate pixels with action. For instance, you can train a robot car to avoid trees by showing it a lot of pictures of trees, and then the car will learn how to go around the trees. Now, in the past, if you wanted that robot to also avoid benches and people and buildings, you'd have to show the robot a lot of pictures of benches and pictures of trees and pictures of buildings. But now with language, we don't have to go through this additional training step. We can say, okay, you have learned how to avoid trees. Now also avoid people and buildings and benches and animals and anything you want. And this actually gives us much faster way of training models. And it also gives us a wider set of generalizable actions that are available to robots through the use of multimodal models. It's not just about morphology and angles. It's also about forces and torques and what is needed to have the interaction with the world. And so for this reason, watching videos only will not take us to a world where robots will know for sure how to interact with the world. We would need force data, torque data. We would need to know exactly, if you pick up a pitcher of water, what are those forces and torques that are on your joints and on your muscles? And because without that, we can generate fantastical videos that show the correct kinematics but do not have the correct dynamics. And so when it comes to learning the dynamics of interaction, we have extraordinary possibilities, but also challenges because there isn't enough data. However, we are beginning to see research groups that are forming the kind of comprehensive data sets that will really help us get robots to learn how to be in the world in a dynamically coherent way.
How do you use the right data, especially now that AI is generating its own data in some ways?
We have technical solutions for debiasing data sets. We can apply algorithms to a data set and decide whether the data set is biased with respect to a certain range of parameters or not. And so then you can have a data set that is not biased.
I agree. I think one of the really interesting promises of synthetic data, so generative models, they make this new fake data, and sometimes it comes across as that's going to be some worse version of the original data that you started with. It's going to be a cheap proxy. It's going to have artifacts, hallucinations. And that can be true. There can be these downsides. But one thing I'm excited about is that by modeling the data and producing new data from it, you can intervene and change the data distribution. And I think this is exactly what Daniel was talking about. You can remove certain biases by intervening. And we have technical tools that can help us there. You can say that there's a rare part of the data that you want to represent better. Maybe it's a rare disease and you really want to study that disease, and you can oversample that part of the distribution. So by synthetic data, to me, is data that has more opportunity. You can change it, you can make it less toxic if that's what matters for your application.
The field has produced all of these different technical tools that each can be used to push the model in certain directions to achieve particular kinds of balance. But at the end of the day, for a lot of these questions, there is this deeper, higher level question of what are you actually trying to achieve, right? And what is the thing that you're trying to optimize the model for? And I think making sure that when higher level applications are being designed, it's not just about having all of these tools at your fingertips. It's about deciding, what are the parameters that are really important for these applications? What are the possible failure modes? And traditionally, the way we've thought of computer systems is as the kind of system where you have a specification and you can design it and you produce something that satisfies the specification, and then it works. With a lot of these learning-based systems, I think there's a much bigger need of the kind of empirical validation and empirical testing that oftentimes doesn't come quite as natural to people in our community, but it is absolutely essential to make sure that the systems that get deployed actually do what they're supposed to do when they're out in the world being used by real people.
Just a quick question on deepfakes. So are you doing anything to protect us from this?
Two things have changed. So one is that the synthetic images and videos now have gotten so good that a lot of the techniques that we were developing a few years ago just don't work on the current models. And so it's a constant arms race. And I do think that it's important that people keep up with that. We have detectors for the latest models, but it's kind of a grind to keep going through that. And the other thing that has been interesting is that even though these deepfakes have the potential for creating a lot of misinformation and for us losing touch with reality, it seems like we've, as a society, started to develop other types of antidotes to some of that by maybe not trusting as much what we see online. I know that people still probably trust too much what they see online, but I currently feel that socio-technical and policy level interventions are probably going to be more effective at dealing with the advent of deepfakes, and we might have to look at the signature of a piece of media and not just trust the pixels. Not seeing is not necessarily going to be believing. And so even though there are some technical solutions on detecting deepfakes algorithmically, it might be that socio-technical and policy level interventions are more effective.
It's such an exciting moment for generative AI and for AI in general. And the research that is happening at CSAIL covers a lot of the foundational aspects of AI that need to be developed in order for this technology to be applicable to its full potential. At the same time, it's important for us to remember that generative AI is just one component of the AI ecosystem. In AI, we have predictive and classifying AI, we have generative AI, we have optimizing AI, we have deciding AI. And most business problems are at the intersection of solutions across these different set of techniques. And we will talk more about this and about how generative AI combines with other kinds of AI at the future office hours. For now, thank you very much for joining us, and see you at the next CSAIL office hours.